So hopefully people start joining in a little bit more as we get started here. Not a lot of people here because of the weather, but we'll kind of keep pushing on. Couple things I want to mention before we get going. There will be a Connect and another Excel assignment I'll post when I get back to my office today. Those will be due at the end of the day, Friday next week. They've been over material we've already covered. After today, we'll pretty much have all the material we need to cover that Excel assignment, and the majority of the questions on the Connect, maybe the last 2 or 3, might not have the material covered until the end of class Thursday. So I would start working on those this week because I'll also be putting out some practice exams on Canvas, which as we're getting kind of closer to that exam date, those are we'll probably next week will be a lot of reviews, so I'll go over a lot of those problems in class, but just wanted to get them out there early in case people, depending on your schedule, kind of have a little extra time to look at those. Other than that, are there any questions for me before we get going here? And also, I think we got all the tech issues hopefully solved, so I think we're good to go today. So there's no questions. Kind of jump into it. So I'll go over the kind of first part of what we're talking about today, probably relatively quickly. It's a lot of review, just painted in a different context. So let me put this down here. So up to this point, we've kind of been looking at variables that have already been recorded. So now we're going to start talking about things we're going to call random variables, which is we haven't seen the outcome yet. So we know what the different possible outcomes could be. It hasn't been realized yet. So it's going to be very similar to what we were talking about with regular variables. It's just that we're kind of predicting the future. So just like the other quantitative variables we're looking at, we've got discrete and continuous. I'll kind of gloss over this, but the notation we're going to use is capital X to represent whatever this variable X is that we don't know the outcome of yet, right? This random variable X. Okay? Every possible outcome that we could see, we'll kind of start labeling X1, X2, X3. So this is the idea. Let's say I was asking someone at random the number of children in a household. So capital X, the number of children in a household, it's my random variable. I know that I could see the very lowest value I could see is 0. So X1 would be 0. X2 would be I see 1 kid. X3 would be I see 2. So on and so forth. Okay. So we've got these discrete random variables, which is what we'll focus on prior to this first exam. So it's very similar to what we talked about before. Usually it's a smaller finite number of responses where we usually only see integers, right? Or at least there's gaps in between what responses we can see or what types of outcomes we can see. Okay? So this was the number line where we said it could be 0, it could be 4, it could be 8, but it can't be 6.32. Okay? So this is kind of a review of something we already talked about. And this might be the number of times you do something every week, right? So the only possible responses you could see for a variable like that was 0 through 7, right? So you know the outcomes that you could see, but if you're asking a person at random, you don't know which one of those outcomes is going to be realized. Also, if this screen ever goes out, just yell at me because I can't quite see it from my angle. So, so the continuous random variable, I'll kind of hold off on this, but this is just variables that we could see those values in between. Like I said, we'll kind of pick up more on this after this first exam, thinking about continuous random variables. But it's going to be a very similar idea. It's just that we can see the values in between the integers. Okay. So some different types of variables. Family size is the one that I'll probably kind of use to set this up today. So the number of dependents on a tax return. We can't see 1.5 kids, so we're only going to see integer values there. So it's discrete. Distance from a store, right? We think of continuous. We can measure that out to whatever decimal we want. And then here's a unique one that I don't think we've really kind of looked at yet, but we could take a qualitative variable and force it to be quantitative. So if I ask someone, do they own, what types of animals do they own, dogs or cats? They could say I own neither of those. I own only dogs, only cats, or I have both, right? So we could take these qualitative responses and just assign them a number and make this a discrete variable, right? So we'll be thinking about some examples that look like this and really what statistics we would want to calculate if this was the scenario. Any questions on that? Am I sounding okay on Zoom? Hopefully, if I don't, let me know. I can reset the mic. Awesome. Okay. So I've got all these different outcomes, and I know that some are more likely than others, right? So how likely certain outcomes are, right? I want to be able to visualize, maybe using like a graph or a table. And so I want to get this probability distribution, right? So the very basic setup that I'll show you, there is no real functional form. We're more so just assigning probabilities, okay? So this will become a little clearer, I think, when we look at the example, but what's going to assign those probabilities for different outcomes for X is this probability mass function, okay? So basically, I'll plug in a value, say the number of kids in a household is 3. That probability mass function will take that 3 and spit back out at me the probability I see 3 kids in a household, right? That's the idea of what that probability mass function is doing. It's just like any other function where I'm putting in the X value and it's returning to me the Y value. It's just our Y value now is representing a probability, okay? So this probability mass function will start to write as P of capital X, this random variable X, is equal to specific outcomes. So the probability X is equal to 1, the probability X is equal to 2, so on and so forth. As I input those X values, I could then end up with pairs, right? I'll look at the very first outcome, which is I could see 0 kids in a household. I plug that 0 into my probability mass function. It gives me the probability that if I ask someone at random, I see 0 kids in their house. So I then would have these X, Y kind of coordinate pairs, right? Because I would have X is equal to 1, plug that in, I get the probability X is equal to 1. X is 2, plug that into my probability mass function, get the probability X is equal to 2. So once I have all these pairs, well, I'll skip ahead. We'll come back to the conditions. Once I have all these pairs, I'm going to think about it as I'll have a different number of possible outcomes and the probability associated with each one of them. So I'm just jumping ahead to kind of give you an idea of we have all these possible outcomes for the variable X. Here's the probability of each one occurring. So those probabilities have to follow certain rules. The first is if it's a probability, the lowest it can ever be is 0, right? We said the probability that something, if it can never occur, the lowest the probability can be is that the probability is 0, right? Which is like a guarantee that that outcome doesn't happen. Okay? The highest it can be, if it was with certainty, is the probability could be 1, right? We said if something's going to happen with 100% certainty, our probability would be 1. Therefore, the probabilities that we're going to see have to be somewhere in that range, right? They can't be outside of that range from 0 to 1. So similar to some other ideas we've talked about with relative frequencies, which we said represented probabilities, but also when we're thinking about the entire experimental outcome space and, what did that space represent? Well, that really represented adding up the probability of every single possible outcome. And we said that experimental outcome space should be 1, or that relative frequencies should all add up to 1 because it covers every possible outcome. So the same idea is going to hold true here. Once I look at all the values of X and get the probability of seeing each one of those values, when I add all those probabilities up, starting with the first outcome going to the last, those should add up to 1. Okay? Like I said, this is similar to what we talked about just with relative frequencies and then the entire experimental outcome space here. And we'll see this once we start working some examples. The next thing that we also talked about with relative frequencies is that we could do cumulative relative frequencies. So very similar idea. We're also going to have a cumulative mass function. So maybe I don't want the probability I see exactly with 0 kids or exactly 2 kids in a household. I might want the probability I see 3 or fewer kids, right? So the idea of cumulative was look at the current outcome and add up the probability of that to all the probabilities from the outcomes below it, right? So I'll give you I'll kind of go off and write some stuff here in a second for this, but let's finish this out a little bit. So this cumulative mass function, as I am looking at the really low values of X, right, the smallest values, that cumulative mass function is going to be really close to 0, right? Because there's not many outcomes that are below the lowest values. If I think about the number of kids in a household, the cumulative mass function for 1, well, there's not going to be as many kids, households that have 0 or 1 children. But if I'm looking at X is equal to, 15, almost every household has 15 or fewer children, right? So as I get to higher X values, that cumulative mass function should start getting closer and closer to 1. So the idea of this cumulative mass function, and let's go here and here and see if this this will work. Can I get this to autofocus for me? I have to hear a little beep so I can get this to autofocus. There we go. So, with a cumulative mass function, what I'm really thinking about, is I'll take whatever x value I'm interested in and say the cumulative mass function tells me the probability I see that outcome or anything less, right? So less than or equal to. Well, another way we could think about writing this is the probability I see exactly 3 kids in a house, or, right, using that union, or I see exactly 2, or I see exactly 1. I'm going to run out of room here, but or I see x is equal to 0. Right? Now, when I'm looking for the probability of unions, we said that was simply add up the probability of each event and subtract the intersection. Well, here we have an interesting situation where even if we just think about 2 of these outcomes, what's the probability I see exactly 2 kids in a household and I see exactly 3 kids in a household? Well, it's impossible, right? It has to be one or the other. Like if I'm looking for the exact number of kids, right, it can either be 2, it could be 3, it could be 5, but it can't be 5 and 3 at the same time. So we know that these intersections are 0, or said differently, our definition, these are mutually exclusive, right? So that makes our life a little bit easier because then when we want to find unions, it's just the probabilities of the events added up because there's nothing we're double counting, there's no intersections. I'm going to switch colors. I think my black marker might be running out here. So really we can rewrite, so I'll keep this on the same screen. We can rewrite this union as the probability I see x equal to 3 plus the probability I see x is equal to 2 plus the probability x is equal to 1 plus the probability x is equal to 0, right? So cumulative mass function is just take that x value that was kind of your cutoff of 3, take that probability and add the probabilities of every outcome below it. The outcomes below it, in this example, 2, 1, and 0, okay? So don't forget about 0. A lot of times in these examples, the lowest value we could see is 0, okay? Any questions on that? I think that should make sense based off things we've already done. Let's go here. Let's see if this is working. If I can switch, there we go. Is this showing up to the, yeah, awesome, perfect. So if I think about an example where maybe I'm looking at the number of new hires for a company, right? Now, our probability mass function, I said, isn't going to take a functional form. And more often than not, we're going to use the empirical assignment of probabilities to basically create our own probability mass function. So I look here and the number of years I had no new hires from this company was 0 years. Maybe it was a relatively small company, so the number of years they had only 1 hire was 2 years. They only hired exactly 2 people in 1 year, but there were 7 years in which they hired exactly 3 people, right? And so on and so forth. Okay? So I have 35 years of data. So if I want to turn these frequencies into probabilities, what's one thing I could do? So hopefully, all right, I know we missed a little bit of class on Thursday, but I posted the additional Excel tutorial of how to build those contingency tables, which will look very similar to that Excel assignment I'll post today. If I want to go from frequencies to probabilities, how could I do that? Count maybe on someone from Zoom here, right? See if we can kind of get someone to answer me here. How would I go from frequencies to probabilities? Nobody? Yeah, so someone said it. Divide by the total number of observations, right? Well, I've got 35 years of data here, so if I add up my frequencies, my total number of observations is 35. Divide each one of these frequencies by 35, and now we've got the different possible outcomes we could see for x, this random variable, and the probability of seeing each one of those outcomes, which is this essentially becomes my probability mass function schedule, if you want to kind of call it that. Okay. So if I tell you, or I guess if you tell me a possible outcome for x, I can use this as my probability mass function and tell you the probability you see that certain outcome for x, or that certain number of hires in this example. okay? So one rule we talked about is, first of all these should be between 0 and 1, which they are, right? Some of them are 0, but we said that they could be that. If I take every possible outcome and I add up the probability of all those outcomes, the probability of all those outcomes should add up to 1 down here. Right? That was another rule we said. Sure enough, they do. So, we didn't make a mistake here, or at least not an egregious one, right? I could then take all of these x values, plot them on the x-axis, and at 0, draw a bar that goes up to the probability of 0. At the x outcome of 1, draw a bar that goes up to the y on the y-axis up to 0.06. The x value of 2, draw a bar that goes up to 0.03. And basically very similar to what we were doing with histograms, right? Or even when we were trying to look at a distribution of qualitative data, create this little bar chart. And I can kind of quickly see the distribution for the new number of hires, right? 3 and 4, very clearly the most common number of hires. Occasionally we've had some boom years where I hire kind of these higher number of new hires. And then very seldom do I have, very small numbers of new hires, okay? And if I'm trying to think about where's the middle of this distribution, well, I mean, these are the most common outcomes, 3 and 4, but there's a couple more outcomes above that than there are below it. So I don't know, somewhere around 5, 4, something like that. And I'm just trying to guess where the middle of this distribution is. Okay. Well, guessing, and look, like I said, I'm kind of going over this quick because this is really very similar to what we did with histograms, right? And relative frequencies. It's just now, instead of calling them relative frequencies, they represent the probabilities of seeing different outcomes for this discrete random variable. Right? It's really kind of semantics here. So if I'm looking for the middle part of that distribution, what's a statistic we've talked about that kind of gives a measure of that? The mean, right? So how do we find the mean of a discrete random variable, or what we'll sometimes call instead the expected value? So those two terms are kind of interchangeable. If we're thinking about the mean of a discrete random variable, we're really trying to come up with a predicted middle of the outcomes, right? Because this thing hasn't occurred yet, right? These outcomes we haven't realized. We just know that different ones have different probabilities of occurring. So we'll write this as kind of mu of this random variable x, right? That's kind of typically how we write the mean. But we can also think about this as our expected value of this random variable x. Okay? So, all we're going to do, it's going to look something very similar. It's going to look very similar to something we've already done, which is I'm going to go through every possible outcome. I'm going to take the value of that outcome and multiply it by the probability that outcome occurs. Once I do that for every single possible outcome, I'll add them all up. So this should look really similar to what we've already done, which was weighted means, right? It's just now for our weights, we're kind of using a certain function, right? That function is this probability mass function that gives me the probability that x is equal to different outcome values. Well, if I simply add up the weights here in my denominator, what's the sum of the probabilities for every possible outcome? I just said earlier on the previous, I think 2 slides ago, the sum of all those probabilities should add up to 1. Yeah, right? So my denominator will always be the sum of the probabilities, which will always be 1. So essentially, I can ignore that denominator. So it's really like a weighted mean where it's become easier, right? Because now I don't have to worry about dividing by the sum of my weights, because the sum of my weights here when I'm using probabilities will always be 1. Right? So very, very similar to what we did with the weighted mean. We'll go through an example here in just a second. So if I think about this new hires data set, here's my possible outcomes. Here's the probability each one occurs. So to find the mean, I would go first outcome of 0 times the probability I see is 0, which is 0. That one's kind of easy, 0 times 0, plus the next outcome of 1 times 0.06, plus the next outcome of 2 times the probability it occurs, 0.03, so on and so forth. If I add all these up, if I kind of write this out, right, they'll add up to 5.14. Okay? So same process we were using for the weighted mean, but I don't have to divide by the sum of my weights here. So any questions on that before we keep moving? Yeah. Just a second, pull up my clock pulled up. So if this is our mean, right? you can also imagine we can find the variance of a discrete random variable. So once again, this is going to look very similar to the weighted variance that we did. So what we're going to do is go through every possible outcome, subtract the mean from that outcome, square that value, then whatever that deviation squared is, multiply it by the probability we saw that X outcome occur. Go down to the next outcome, do the exact same thing. Once we do this for every possible outcome, we'll add them all up. Now, usually we'd have to divide by the sum of our weights, but the sum of our weights here, once again, sum of the probabilities should just be 1. Okay? So it's like the weighted variance, but a little bit easier. We don't have to worry about that denominator. If I ever want to calculate the standard deviation, the only additional step I need to take is I simply take the square root of the variance, right? So same principle applies as what we've been talking about before. And really all the principles of a weighted variance and all the principles of a weighted mean kind of apply. You know, in the weighted mean, the values or the outcomes that kind of influence it the most will be the ones that are most likely to occur or have the highest probability of occurring, because those probabilities are our weights, right? So they'll be weighted the most here. 3 and 4 would be weighted the most. So they'd influence the mean the most. Once again, our variance, right? We're trying to kind of capture the average deviation from the middle part of this set of data set now, the middle part of this discrete random variable. So if we're thinking about what this looks like with that new higher data, we'll take that very first outcome of 0. We'll subtract the mean of 5.14. We'll square that deviation, then multiply it by the probability we saw that outcome of 0. Now that was not very interesting because 0 times anything is 0. For the next possible outcome, 1, we'll subtract that mean of 5.14, square it, and then multiply it by the probability we saw 1 occur, which was at 0.06. Then just go through and do that for every single observation, right? Add them all in. If we do that, we should get around 5.38, okay? Any questions on this? Like I said, it's kind of a review of how we do weighted variances here. Okay? Now, kind of writing it out like this is a little bit of a mess, and especially with smaller data sets. I'll kind of show you a trick here in the next example, how we could do this and maybe find some intermediate calculations so this isn't like all entered in one line or a calculator and we accidentally forget a parenthesis and screw up the answer. Right? So let's say I had this data set where it's, and this is kind of wild, I put this in millions. I probably should have put it in thousands to make a little bit more sense for most jobs. But let's say, you know, we've got kind of the top person, you know, not probably a CEO, but kind of the top day trader at some company. And depending on how he performs for this massive investment company, they tell them, you're going to get a bonus, and it's going to be one of these 4 amounts, depending on how you perform. And we put it in millions to make it kind of seem wild. So you get $0 with a probability of 0.2. You have $3 million bonus. The probability of you doing that is 0.4, 6 million, 10 million, and their associated probabilities. So if I'm thinking about the mean of this discrete random variable, right away, if I look here, what are the 2 most likely outcomes? So I look at my probabilities, 6 and 3 million are the 2 most likely outcomes here. So if I'm trying to guess where the middle of the data is, well, here's the most likely outcomes, and they're kind of in the middle of all my possible outcomes, so it's probably going to be somewhere in this range, right? Probably somewhere between 3 and 6 million, which means A and B don't really make a lot of sense for me here. In order for A to be the correct answer, what that would have to mean is that on average, right, the outcome of this discrete random variable is that someone only gets $250,000, which would mean more often than not, they're probably getting 0, right? So if that's the case, the probability of seeing 0 should be much higher than 0.2, right? Not the 3rd most likely outcome. It should be that 0 would be the most likely outcome. So A and B don't make a lot of sense for us here. But if we wanted to actually calculate what this is, what I would do is right next to this data, I'm going to kind of do this on the, so I'm going to insert a column to the right here and make this a little bit bigger. So all I'm going to do is go through and every single outcome, take whatever the value for X is and multiply it by the probability that I see that value for X. So the first one, 10 times 0.15 is 1.5. 6 times 0.25 actually ends up also being 1.5. And then 3 times 0.4 is 1.2, and 0 times 0.2 is 0. Now that I have these intermediate calculations done, the last step is add these all up. If I add these all up, I'll get 4.2 million, right? So kind of creating this additional column is a way in which you don't have to enter that all in like one line in your calculator. You can kind of break it down into parts, right? But whatever way is easiest for you, I just always like to kind of show it that way. I think it makes a little more sense to some people. Okay? So we've got that mean of 4.2. Make sure there's no questions there. What if I wanted to find the variance with this data set, right? Well, first of all, if I look at these options, which ones can I rule, or what answer or answers can I rule out right away? Make it a little bit harder, why? Can I get anybody out there want to? So what answer could I reject here as being a possible or correct answer? So someone's saying B, yeah. So why would B? Why can I rule out the negative answer? Remember, we said the variance, right? What would the lowest variance that we could ever see be, right? Yeah, someone's saying it's squared, right? Part of the calculation is that we're squaring that deviation. So whether or not the outcome is above or below the mean, when you square that, a negative times a negative and a positive times a positive, it's always gonna be a positive answer. So you're always getting positive amounts added to your numerator here. I mean, you don't have a denominator, so just add it to the function here. But the other thing we think about is the lowest I could add from any one observation would be if it was exactly equal to that mean. So the lowest my variance could ever be is 0. Right? Now we talked about before, if the lowest my variance, if I see a variance of 0, it's kind of a hard thought experiment, but before we said it would be a data set where every single observation was the exact same value. That way, no observation could deviate at all from the mean. So with a discrete random variable, it's kind of difficult to think about, but what that would look like is, well, if nothing can deviate from the mean, it would have to be the only outcomes I could see, like in this example, for instance, would be I only ever see 3 million, which if that's the only thing I ever see, what's the probability that I would see 3 million? It would be exactly 1, right? So if the variance was 0, it would be a very uninteresting example, right? We'd have one outcome that would happen with certainty, right? So we're never probably going to see a variance of 0. We can't see variances that are negative, so it's going to have to be something that's positive. So A, C, or D here. Now from there, oops, we're just going to have to calculate it. So once again, I'll kind of add in an additional column here and show you what if I had done this, kind of calculating my intermediate values, which now will be take the x value, subtract the mean, and square it, and then multiply it by the probability x is equal to whatever that x value was. Here, let me shift these around a little bit so we can get this all in one line. There we go, right? So that deviation from the mean squared times the probability that x outcome occurs. So for this first one, it would be something like take 10 minus that mean of 4.2, right? Square that value, and then multiply it by the probability we saw that 10 occur. Right? I'll then go through, do this for every single observation, right? Add them all up. Once I do that, I don't have a denominator because I said here the sum of the probabilities is 1. So once I do that, add them all up, I'll be done, right? There's nothing to divide by because my weights are probabilities. So I think if I end up computing this out, if you just want to kind of check yourself, the answer ends up being this 9.96. Okay? If I then wanted the standard deviation, what's the only other thing I'd have to do? Well, now that I've got the variance, simply take the square root, right? All right. So that's kind of a smaller example, kind of showing you how you can break it down to make it a little bit easier than kind of putting all this on one line of your calculator or Excel or whatever you're using to calculate that. Any questions at this point before we keep moving? I don't want to click that. Okay. So, by the way, I don't know if anyone recognizes these clips or the reference of sine capital. But this is a movie I suggest to business school students in particular. It's called The Big Short. If you guys haven't watched it, it's just a really good, entertaining movie, but it kind of chronicles the financial crisis with mortgage-backed bonds and explains it in a very easy to understand way, like I would say like a layman's terms way. My sister enjoyed this movie and found it interesting, could follow along with it. And she's like the most bohemian hippie anthropologist like you can imagine. So like nothing about numbers or finance, and she followed it and enjoyed it. So I always suggest if you're in the business school, you should watch this movie. It just gives you an idea about how to even discuss or think about what was going on in that financial crisis. Okay, like I did my duty there as an economist. So we're going to move on to kind of the next topic, which is the binomial distribution. So we'll cover two specific types of discrete random variables. The first one is going to be this binomial distribution. Okay? So the setup is going to be anytime we have something where we have n trials, right, and they're identical. So we have this experiment, we run it over and over and over again. We run it up to n times, right? So after we run this, we can think of each time we run the experiment, there's only two outcomes, okay? So this is like binary, right? I'll see either a success, and that's really just what I'm looking for, and the failure, which is that what I'm looking for doesn't occur. So this could be as simple as I flip a coin. I want to know what's the probability it comes up heads. There I've defined my success as seeing a heads come up on this coin flip. Failure would be seeing the tails, right? Or the other outcome. So let's say I flip it 100 times, right? Each time I flip it, the probability I see a heads is 0.5, right? If it's just a regular fair coin. So the probability of success, it has to be identical across trials. So even though I'm flipping this coin 100 times, on any one coin flip, the probability I see it come up heads is the same, right? 0.5. And then each trial needs to be independent. So we talked about with coin flips, this is true. Even if I get 3 tails in a row or 3 heads in a row, what's the probability I get a heads in the fourth coin flip? Still 0.5, right? They're independent trials or independent experiments. Well, then what we might be interested in is, okay, what's the probability mass function for seeing a different number of successes? So I'm flipping this coin 100 times. What's the probability I get exactly 50 out of the 100 to be heads? Because that's not 100%, right? A lot of the times I flip a coin 100 times, I'm going to see 51, 54, 48, right? There's all these different possible numbers of heads I could see, and it's definitely more likely that I'll see some of them, right? It's more likely I'll get 50 out of 100 than getting 90 out of 100 heads, right? So I want a function that will give me the probability of seeing a different number of heads, right? Or a different number of successes. So that's really what that binomial is going to do for us. It's going to give us the probability out of n trials that we see a certain number of successes. Right? So that function, that probability mass function, actually has a functional form, right? Before, we didn't have like a plus b times x squared. We didn't have an actual function. Now we do, right? So this is a little bit nasty on its head. We'll kind of go through the parts of it, and hopefully I'll kind of make it a little bit easier. And once we work through some examples, I think we'll maybe be less concerned about this. So n here is just going to be the number of trials, and that matters, right? If I'm finding the probability that I see 50 successes, right, or that heads comes up 50 times, well, that probability is going to be very different if I flip the coin 100 times versus 50 times, right? So the number of trials matters, so that's going to be one of our components. The number of successes we're interested in, well, obviously, like that has to be one of the inputs into this function. So x is going to be in there, the number of successes we want to find the probability of. And then the probability of success on any one trial, right? That, in our case of flipping a coin, the 0.5, that would be p, right? The probability of success in any one trial, or the probability to get a heads on any one coin flip, okay? The only thing, so other than that, so we've defined the kind of the 3 things we need to plug in here. This part, I think, is relatively easy. Like we're doing some subtraction, we're doing some raising the things to a certain power. The thing we might not recognize is this exclamation point, right? Why am I so excited about the number of trials here? So when we write this exclamation point in math, and also that was like a cheesy dad joke. I hope someone at least kind of got somewhat of a chuckle out of that. But that factorial, right, that exclamation point, we'll call a factorial. right? All it means, right, here's the formal definition of it, but the best way to think about it is, if I have 10 factorial, it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So you just start at that number and you multiply all the way down to 1, okay? So once we know that, this isn't as scary. If you want to try to find this on your calculator, usually on like a TI 80 something or above, like an 80, I don't know where I think 83 is the most common one, but usually I believe there's a math button. I think it's on the right-hand side of the calculator, and you might have to hit second, and then it might be like the kind of above it. Then you go over to the PRB or PROB, I forget what the heading is, it's the third one over, and then underneath that category, you'll see the exclamation point. Different calculators are different. A lot of the times you're looking for, like I said, a math button, or like a lot of them, there's a PRB, or kind of representing probability button. And sometimes you'll have to hit second in order to get that. But then under those categories of math or PRB or PROB, you'll usually find that factorial. Occasionally I've seen it as like just a button on the calculator where you hit second and then it's directly above, one of the buttons, but that's a little bit more rare. So look for that factorial in your calculator. If you can't find it, here's the steps to take. I want you to reach out to me and I'll help you find it. But before you do that, because this is honestly what I'm going to do when you first send me an email, Google the type of calculator you have and factorial button, and see if you can find some instructions of how to find it on your calculator. If you're not able to find anything, then reach out to me, and let's make sure that everybody knows where that's at, especially kind of going into this next homework assignment and then kind of consequently the exam. Okay? Any questions over or anything up to this point? I want to make sure we have a good understanding of everything in this equation before we go to some examples. Take that as we're okay. Another weird thing here, maybe if you have time at the end, we'll Google, kind of look at the proof, but one thing that's kind of weird is if we ever have a 0 factorial, we actually that ends up computing, we'll use a 1 there, okay? So anytime we have 0 factorial, we'll just use a 1, okay? So that's only the only weird thing there. Also, something that could happen, we'll look at an example up here today. What if I raise something to the 0 power? Anytime I raise something to the 0 power, doesn't matter if it's 100 to the 0 power or 10 to the 0 power, that should just be 1, okay? So 0 factorial is equal to 1, and anything to that 0 power, right, we can kind of just treat as a 1, okay? All right, so moving forward, did you check me on that? it worked, right? Yeah, so let's look at an example. We're flipping a coin 10 times, right? And it's not a fair coin. So the probability that comes up heads is only 0.4. It's weighted, right? So what's the probability 4 of those 10 coin flips come up heads? So I think intuitively, when we see this, we think, oh, well, we're flipping a coin 10 times. The probability on any one coin flip that comes up heads is 0.4. Like, it's very, very likely that we see 4 of the 10, right? That's what we on average should see. And that's right. That's the intuitive way to think about it. But it's not going to, we're not going to get 4 out of 10 with 100% certainty. So how low is that probability? Because if I flip a coin 10 times, it's very likely I only get 3 heads, I get 5 heads, I get 6. So we're going to use that probability mass function. Our number of trials, we're running this experiment, we're flipping this coin 10 times. The probability that I'm interested in is that I see 4 successes, so my X is 4, and the probability I get a heads on any one coin flip or a success on any one coin flip would be that 0.4. Okay? So I've identified those 3 components. From there, it's just a matter of plugging those values in to my probability mass function for a binomial example. So everywhere there's an N, I plug 10 in. Everywhere there's an X, I plug 4 in. Everywhere there's, where are they? Here, P, I plug that 0.4 in. So at this point, it's just a matter of getting this entered into our calculator, and we can find that the probability we get 4 out of 10 is around 25%, or a probability of 0.25. Now, I don't think once you get this plugged in, it's really how can I make sure I'm making fewer mistakes entering this into my calculator or in Excel or whatever I'm using. Well, first of all, don't worry about all these parentheses. You do the simple math in your head. hopefully you know that 10 minus 4 is 6, right? So instead of putting parentheses 10 minus 4 parentheses, just put a 6 in there, right? You know that's what it is. 10 minus 4, that's just 6. 1 minus 0.4, 0.6. So do the easy math first before you try plugging this like into your calculator, and that'll solve a lot of problems, right? You have to worry about a lot fewer parentheses. From there, the only other issue might be, well, what if I can't find my factorial button, right? So let's say I can't find my factorial button, right? How would I rewrite this? So let's see. Oh, hopefully this pops up. Is this showing? All right, there we go. So if I'm thinking about, I'm just going to write the factorial part so we can start to understand that. So I think it was 10 factorial over 4 factorial times 6 factorial, right? The 10 minus 4, I just put in 6 to the easy math. So if I write this out, 10 times 9 times 8 times 7, I'm not going to keep talking because it probably just gets annoying at that point, but we write it all out. 4 times 3 times 2 is 1. And then 6 factorial is 6 times 5 all the way down to 1, right? Well, notice, because we're multiplying everything here is going to cancel. And this simply, I can enter in my calculator, is 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. Right? So even if I can't find my factorial button, I should be able to do this one relatively easy if I just write it out and realize that a lot of things are going to cancel. But maybe you don't like that and you start using your factorial button. You get pretty comfortable with it. What's something that you could run into a problem with? Well, let's say I had some crazy example where I flip a coin 100 times and I'm interested in what's the probability I see exactly 99 coin flips come up heads out of those 100. I know that probability is probably relatively small, right? Especially if I'm using a regular coin where the probability of heads is 0.5 on any one flip. So I start plugging these values into my binomial, and that very first part with the factorials will look something like this. Okay. But if I write this out, first of all, 100 minus 99 is 1 factorial. What's 1 factorial? Well, 1 times 1. I mean, it's kind of weird that 0 and 1 factorial both end up just being treated as 1, but that's how we use it. So if I've got, I've got 1 here, and then if I just kind of write out the first few parts of these, all right, 99 times 98 times 97, and then times 1 there. Oh, let me move this here. Notice everything here is going to cancel, and I'm going to end up with 100 divided by 1. So all of this is just 100. Right? So I write these out, especially for these really large n and x values. Usually there's a lot I can cancel and kind of make this a lot more easy to enter into my calculator. If I try to put this into my calculator with the factorial button, you're going to run into a problem. I think the highest you can go is somewhere in the 60s on like a TI-83, and then smaller calculators obviously don't have the capability because 60 times 59 times 58 times, that starts to get really, really big, right? So we can't really use a calculator to do this, but if we just simply write this out and realize what cancels, this is really easy to do by hand. Okay? So anytime I throw out an example at you where you see like a really high n or a really high x, like over 60, you know there's probably something you can do to cancel to make this a lot more manageable as opposed to like, well, I can't calculate it. My calculator says error, right? So be kind of looking out for examples like that. Any questions on that? And obviously, I was just focusing on the first part of that binomial equation. We would still have like this times all, the probability raised to the x power and whatever else is in there. Okay. All right. So we'll go back here to the slides. So what if I have, where are we at in time? Oh, good. What if I have a different example? So let's say I'm thinking about the Wall Street Journal says 30% of adults have a 4-year college degree. And I select 5 of them at random. what's the probability that exactly 3 of them have a college degree, right? This one's a little bit different, but here I'm looking at 5 different adults and asking them if they have a college degree. So my success failure is, well, they either say they have a degree or they don't, right? There's only 2 outcomes. So I'm looking for the probability that they have a degree, so that's my success. The failure is they don't. I'm looking at 5 individuals, so I'm going to think about each time I ask this question or run this experiment of asking this question, I'm doing it 5 times. That's my number of trials. And then the probability any one person I ask has a degree, well, based off of some empirical data we have, we know that's about 30% or a probability of 0.3. So I want to know what's the probability exactly 3 of these 5 have a degree. So I'm going to try to find the probability x is equal to 3. So now I've got my number of trials n, my number of successes x that I'm interested in, which is 3, and my probability of success in any one trial, which is 0.3. Okay. So I'm just going to have identified those 3 things. It's just a matter of plugging them into this equation, right? And getting comfortable entering this into our calculator. Okay. Once again, if we write this one out, write the factorials out, this becomes pretty easy math here pretty quick. Okay. So where do I want to go with? Well, I think, all right, I have an idea. So let's instead do same sort of setup, right? Hopefully this isn't too bad. I should have paused there, but are there any questions on that? It's just a matter of getting those 3 things you identified, plugging in this equation, and getting comfortable using your calculator. So what if we have the same setup, but now what I'm interested in is out of those 5 people, what's the probability that 4 of them have a college degree? Okay. So the probability that 4 of them have a college degree. Well, this is where I'm going to set something up that we haven't talked about yet. Okay. So intuitively, I think I might jump ahead here. All right. So here we have the equation for the mean of our binomial distribution. But intuitively, if I have 100 people, right, and 30% of adults have a college degree, on average, out of those 100 people, how many will have a college degree? Well, if it's out of 100 and 30% of people have a degree, on average, 30 people, yeah. Right? Or if I have 10 people, right? On average, if 30% of people have a degree, out of 10 people, how many people on average would have a degree? 3 out of 10, yeah, right? So what you're doing there intuitively, I gave you some easier numbers to think about, but what you're doing is you're just taking the number of people, multiplying that by the probability that any one person has a degree. Or the number of trials, that was the number of people, times the probability of success. And their probability was, probably someone had a degree of 30% or 0.3, right? Sorry, I shouldn't have said 30% there. 0.3, it's a probability. So I think we can kind of come up with this mean intuitively, right? So let's think about, going back to this example then, if I found the probability that x is equal to 3 is 0.13, right? Let me give you an idea here. So when I'm intuitively finding the mean with a binomial distribution, when I was saying like out of 100 coin flips, like the most common outcome we would see is 50, right? Now we could see 51, we could see 52, 46, but 50 will be the most likely outcome. And really what was 50 there? 50 would have been your mean. Out of 100 coin flips, probability of success is 0.5, so n times p would be 50. Right? So we're thinking about this distribution, right? We're thinking about 50, thinking about the coin flips now, is going to be the most likely outcome, but it would also be pretty likely that we see 51 or 49. And it's still pretty likely, but a little less likely we see 48 and 52. And then kind of as we move in either direction, away from that mean, the probabilities are declining, right? So we can come up with this mean. That will be the most likely outcome. Right? As I move further from that mean, the probability of those outcomes becomes less and less likely. We use a coin flip example, right? Well, what would be the most unlikely outcomes? Either I get all heads or I see all tails from those 100 coin flips, right? And then as I move towards 50, those values become a little more likely. Well, we can do this no matter what type of example we're looking at. So the one with college students or college people having a college degree, my N was 5 people, probability of success is 0.3. So there my mean, N times P, right, would just be 1.5. So the most likely outcome for me to see is 1.5. Well, here now I've got an issue. Right before, I could see exactly 50 heads. Here, well, I can either see 0, 1, 2, 3, 4, or exactly 5 people have a degree. Right? I can't see 1.5%, you know. Oh. So anytime I don't have an integer for my mean, it's really just telling me that the outcomes that are most likely are going to be here, 1 and 2, right? The two integers on either side of that mean, right? And then as I move further from that mean, right, the probabilities will start to fall, okay? Here's an example, though, where I'm kind of limited on the left side, right? Because the lowest I can see is 0. So we just found the probability of 3. Remember, what's on this y-axis? Well, that's my probabilities, right? So I just found probability of 3 was something like, I think, 0.13. So that I know the probability that 4 out of the 5 have a degree has to be less than that, right? And intuitively, that makes sense, right? If on average, 1.5 people, right, 30% of people have a degree, we'll put this in a little bit easier. Instead of 5 people, let's do 10, right? Out of 10 people, on average, you would see 3 out of the 10 have a degree. Well, then it makes it a little less likely I see 4 out of the 10, a little less likely I see 5 out of the 10. By the time I get to 10 out of the 10 people have a college degree, well, that's a very low probability, right? So if I kind of continue this out, it's a very low probability. So anytime I'm moving away from that mean, I know the probabilities are declining, so the probability I see 4 has to be less than 0.13. Okay? Sure enough, if I go to that example where I've now changed it to what's the probability exactly 4 people have a degree, well, the only outcome here that's less than 0.13 is 0.028. If I plug in those values, right, I'm looking for x is equal to 4, number of trials was 5, probability of success in any one trial was 0.3, I end up getting that 0.028, right? But I knew, just looking at these answers, knowing the probability that 3 was 0.13, I know the probability that I see 4 out of the 5 have a degree has to be lower. There's only one answer that meets that criteria. But if I didn't have this prior information, I could have went ahead and plugged everything in and still computed it. Okay? So what has to be true about the probability of 5? It's going to be even lower than this, so it's going to be really, really close to 0 probably, right? If going from 3 to 4, the probability fell from 0.3 to 0.028, when I go from 4 to 5, I'm going to be really, really close to 0 there, okay? Any questions on that before we keep moving? Okay. Here's something a little bit different. So what's the probability that at least 3 out of the 5 have a college degree? Right? So what are we saying with a probability of at least 3 out of 5? Well, that means we could see 3 people have a degree, or 4 people, or exactly 5 people have a degree. So we're looking for 3 different outcomes. So I think the easiest way to do these is write out what you're looking for. So if I'm not looking for the probability x is equal to one number, anytime I have x is equal to one number, I'm using the equation one time and finding that probability. However, what if I had something like this where I say, well, what's the probability that x is at least 3 or greater than or equal to 3? So write down what you're looking for and then just write out all the outcomes that meet that criteria. So this, probably x is greater than or equal to 3, would just be the probability x is equal to 3 plus the probability that x is equal to 4 plus the probability x is equal to 5. Well, if I only have 5 trials, that's where I stop. All right? Okay. And now, yeah, it's a little bit of a pain because every time I want the probability x is exactly equal to one number, I basically have to use that binomial equation 1, 2, 3 times, right? With 3 different x values. So, this is a little bit of a pain, but we can do this, right? In fact, we already found these already, right? The probability was 3 was what? 0.13. Probability was 4 is 0.028. So now let's just do x is equal to 5. Right? So I'll go ahead and write this out. I think there's a slide for it, but we'll write everything out. Our n was what? N was 5. X is now 5. And p was 0.3. So n factorial over x factorial n minus x factorial, probability of success to the x power times 1 minus the probability of success to the n minus x power. Okay. Well, let's do the simple math here. 5 minus 5 is what? 0. Okay. 5 minus 5 down here is also 0. So, I'm off the screen here. So 5 factorial over 5 factorial times 0 factorial, 0.3 to the 5th. I shouldn't even have put this in parentheses, but 0.7 to the 0 power. Well, we said anything to the 0 power is 1. Multiplying anything by 1, I can kind of ignore this. Right? 0 factorial is 1. 5 factorial with 5 factorial cancels. I've got basically this guy over here also represents a 1. So really, this simplifies down to simply being 0.3 to the 5th. Okay? We'll go over this here in a second, why that's the case. But for now, that is kind of a nice thing. When you want to look for the probability that all trials are a success, the math becomes a lot easier. A lot of these things cancel. Yep, so this is going to be 1. So this cancels, and you'd have like 1 over 1, which is 1. So a lot of 1s there. And then we could enter this into our calculator, whatever that ends up being. I'm guessing I have it on the slides here, right? 0.002, right? So I just add these 3 up, and I get the probability I see 3 or more is 0.162. Now, going back, this simplified down to basically, this was just the probability of success to whatever number of successes I was looking for. And that only was the case when the number of successes was equal to the number of trials. So this was the idea, if you can kind of remember, we talked about the probability of A and B. If events are independent, that should just be the probability of A times the probability of B, right? So if I'm looking for the probability, I get the first person I ask has a college degree, the second person I ask has a college degree, the third person, well, each time that's a probability of 0.3. So when I think about the first person and the second person has a degree and the third, all I'm really doing is taking that probability of success and multiplying it by however many trials, right? Because every trial I was running, I was interested in, was that a success, right? Was that the thing that I define as success? So really, we would have spent, right, p to the x power there, right? And that's simplified down. So that was like when we wanted to find the probability that roulette table came up black 26 times in a row. All we did was take the probability of success in any one spin and raise it to the power of that every single one of those 26 spins would have been the outcome of black. Okay. But it's kind of relating old things we've talked about that really are kind of floating on behind the scenes here when we're using that binomial equation. Okay. Another thing to point out with that last example, if I know the probability x is greater than or equal to 3, hopefully I get this number right. I think it was 0.162 we had in the slides there. What is the probability x is less than 3? Well, I could, like I did before, write this out. What are all the outcomes that fit this criteria? I could have taken the probability x is equal to, well, the first outcome that meets this criteria would be x is equal to what? 2, right? Because this is discrete. So this would be the probability x is equal to 2 plus the probability x is equal to 1 plus the probability x is equal to 0, right? I could go through, the problem with that is, if I write that out, well, now I'm going to have to use that binomial equation 3 more times for 3 more different x values. You got a lot more work to do. But notice, if I define this as event A, what would the complement of that be? Well, it's everything that outcome that wouldn't be an A. It's actually just x being less than 3. So I've got an event and its complement. If I know the probability of A is 0.162, we said we can use that complement rule where the probability of a complement is just 1 minus the probability of the event. So just plug in 0.162. 1 minus that, we get about what? About 0.84, 0.838. So we can use that complement rule to save us a lot of time, right? So I'll highlight that even more with this next example. So let's say I want to know what's the probability if I flip a coin 100 times that 99 or fewer of them are heads, right? So what I'm really looking for is what's the probability that x is less than or equal to 99? Well, what fits that criteria? This would be the probability x is equal to 99 plus the probability x is equal to 98, all the way down to the probability x is equal to 0. I don't want to use that binomial equation, 100 times here? That's ridiculous. But what I can do is say, well, look, if this is my event A, then A complement would be that x is greater than 99. What are the only possible outcomes if I flip a coin 100 times that meet this criteria? This is actually just x is equal to 100. Right? That's the only outcome that would meet this criteria. Okay? So if I wanted to find the probability of A, it'd be equal to 1 minus its complement. So when I was looking for this, the probability x is less than or equal to 99, I simply take 1 minus the probability of its complement, where we said the only possible outcome that meets the criteria of being greater than 99 is that x would be 100. So now I only have to use that binomial equation 1 time, then subtract it from 1, and I can find what otherwise looked like a real pain to find, right? Having to use that binomial equation use it 100 times. Okay? Sorry, this thing's trying to focus. Hopefully it's not too blurry. If you have any questions over anything or clarifying, make sure you ask. Okay with that? Yeah, on time. All good. Okay. So, with that in mind, and that's kind of what this was getting at here, right? There's different approaches that we can take. Here, it wouldn't have saved us a lot of work, right? Because we would have had to use the binomial equation 3 times either way. But like in the example I just showed you, sometimes using that complement rule is really, really helpful. Okay? So we already talked a little bit about the mean, how we calculate the mean of this binomial distribution. We also have an equation for the variance. Now, it's not quite as intuitive. And once again, this is one of those things where to go out and find the mathematical proof. It's not overly interesting. But no matter what your number of trials, no matter what your number of, or your probability of success, the variance for a binomial distribution always ends up following this equation. So it's basically the mean, right, n times p, and then times 1 minus p. Okay? And this kind of makes sense in that, like, the variation that I can see in the outcomes that I've realized, right, if I flip a coin 10 times, well, first of all, there's only even 11 possible outcomes I can see, 0 through 10. But if I flip it 100 times, yeah, the probabilities of seeing a lot of the outcomes are low, but I could see any outcome between 0 and 100 technically, right? So the number of trials is going to increase, right, my variance. And then kind of the difference between my probability of success, right? If the probability of something occurring is 0.5, that's going to be a little bit more, give a little bit more dispersion to my data than if the probability is something like 0.000001. Well, if that's how low the probability is, most likely the outcomes I'm going to see, even if I flip a coin 110, or flipping a coin would make sense there. But if I ran the trial 100 times, if the probability is that low, more often than not, the outcomes I'm going to see are either going to be 0 or 1, right, with a probability that low. So the probability of success and the number of trials influence that variance. But really, you'll have a formula sheet. That'll be one of the things I post up there with the practice exam materials. And this will always be how you can calculate the variance for a binomial distribution. The standard deviation, once again, just like every other situation, simply take the square root of the variance. So it's the exact same equation. We have one more step, which is to take the square root. Okay? Any questions on that? How do I want to end class today? Yeah, 10 minutes. Yep, yeah, it's just one more step. It's the same exact calculation, but once you have that variance, it's one more step. You simply just take the square root. Yep. So we'll kind of use the thinking about the mean of a distribution for a binomial distribution. I'm going to show you a couple different graphs here. Right? So let's say I had a number of trials, which was 5. Okay? And the probability of success on any one trial is 0.1. So on average, right, my mean there is n times p. So 5 times 0.1 is 0.5. Okay? Well, I can't see 0.5 as an outcome, but I can see 0 and 1. So 0 and 1, notice, have the highest bars. They're my two most likely outcomes. Now, one of the things that's not intuitive about the binomial distribution is just because our mean is 0.5 doesn't mean 0 and 1 are equally as likely to occur. All right? Because my mean is 0.5, it just means that 0 and 1 are the two most likely out of all the outcomes. So notice here, 0 is much more likely for me to see than 1, but there's still my two most likely outcomes out of all the possible outcomes I could see, or possible number of successes. So as I move further from that mean of 0.5, notice my probabilities start to fall. Okay? Let's say I do the same number of trials, but now the probability I see a success is 0.5. Well, now my mean is 2.5, and this is a unique one where it ends up being that, well, that means 2 and 3 are my two most likely outcomes. And this is a scenario when if n was 5 and the probability of success is 0.5, I get a symmetric distribution so that 2 and 3 are equally as likely. And then as I move away from that mean of 2.5, notice the probability of the outcomes of success that are further from that 2.5 value start to decline, right? Or they're lower. Okay. What if I have the probability of success is 0.9? 5 times 0.9 gives me the mean of 4.5, so it means 4 and 5 are my most likely outcomes. And as I move away from that 4.5 mean, the probability of those numbers of successes further from there start to drop pretty quickly. Okay. But what if I increase the number of trials? So in fact, let's go back here to this example where n is 5 and p is 0.5. What if that probability of success is the same, but I've got a much larger number of trials, 50? Well, there, what would the average outcome be? 50 times 0.5 would be 25. So 25 here is my most likely outcome. And then as I move further away from that mean of 25 in either direction, the probabilities of those outcomes of successes start to fall, actually get pretty close to 0, right? As I move kind of towards 50 and towards 0 there. So it just kind of makes a more continuous, the higher number of trials, it just makes a more continuous kind of looking distribution. And then, here's another one where we've got n is 20, p is 0.2. So there, what should be the most likely outcome? Well, what's the mean? 20 times 0.2 is 4. So notice here, 4 is the most likely outcome. And then as I move away from that mean in either direction, I end up kind of seeing lower probabilities. Okay. Any questions on this before we keep moving? And one thing, just to relate it to stuff we've already talked about, although I doubt this will come up in like a question or anything, but notice that when I have low probabilities, so 0.1 and 0.2, what do my distributions look like? They're actually long right tails or right skewed. Right? What about when I have a high probability, 0.9? I get a left skewed distribution. And then what happens if the probability is exactly 0.5, right? So the interesting thing about the probability being exactly 0.5 means that the probability of success on any one trial is the same as the probability of a failure, right? We have two outcomes. If the probability of one is 0.5, the probability of the other one occurs is 0.5. So that's a unique scenario where our distribution actually becomes symmetric or normal, okay? Normal distribution. You know, if I gave you that college example, hopefully it's pretty easy to find our mean and our variance now. All the mean is right, n times p. So 5 adults times a probability of success of 0.3. We already actually did this. It's going to be 1.5, so it's one of these two. And then from there, it's just a matter of plugging in 5 times 0.3 times 1 minus 0.3. I don't know, if we do that, right, we get 1.05 as our variance. Okay? So these should be easy problems. Like if I ask you a question like a binomial mean and variance on the exam, hopefully those are easy points, all right? Because these should be pretty easy to calculate. Okay, so I hate this slide. I'm going to skip this for today. Shouldn't say I hate it, that's just not my favorite. We'll talk about this in this class. I actually think I'll take a minute or two to kind of end this here and looking at just kind of how we would do this in Excel. So I'll go over the most, oh, actually, I don't want to out of here. I'll switch my video over here. I'm just going to open Excel up, blank sheet, all right? I'll zoom in for us here, and we'll set us up for what we're going to start with next class. So what we're going to do is use this binomial.dist function, okay? So the binom.dist function essentially takes the three things that we usually use, the number of successes, the number of trials, and the probability of success in any one trial. It then plugs them into the equation for us and spits back out at us what that probability of seeing that number of successes would be. So the first thing we tell it is the number of successes we're interested in. So maybe I want to know, well, actually, what was the example I used? I forget. Let's see if I can remember. It was, oh, let's look, because I want to make sure I connect this to the slides. So in the population right now, 6.7% of people are considered millionaires, and we're looking at 100 people. What's the probability exactly 5 are millionaires? Well, on average, how many people out of 100 would be millionaires in the US based off 2018 data? Well, probably success here would be 0.067, so 0.067 times 100, about 6.7 people. So 5 shouldn't be very unlikely, but still not the most likely. So we'll use that binom.dist. We want to know what's the probability 5 people are millionaires, comma, out of, what's our number of trials? We're looking at 100 people. And then comma, what's the probability any one person I select at random is a millionaire? Well, that was that probability of 0.067 or 6.7%. And comma, so for the last thing, if we're looking for the probability of exactly one number of successes, we'll put a 0 there for cumulative because we don't want it to be cumulative, right? We're just looking for the probability of exactly one number of successes. Right? I then close that off. Basically, it does all the math for me. Okay. Now, what if I said, well, what's the probability that exactly, I don't know, 10 people? I could go back in and change this to 10. I'm going to show you something that'll help you on your homework, so it'll help you on the exam. You can kind of get this set up down. Well, let's just set these up in another column over here. So the number of trials is 100. Right? I was interested in 5 successes, and the probability of success is 0.067. Right? What I could do here in this binomial equation was, all right, first I'm going to tell it the number of successes. I have that in this cell here, comma, the number of trials. I have that in this cell here, comma, probability of success on any one trial, in that cell right there. And then we said we're not doing cumulative. We want the probability of exactly 5 people there. So we put in a 0 as that 4th argument. Now, right, when I hit enter, it does the calculation as well, but if I want to go back in, I can start playing around with, what if I want to know the probability of 10 people? Updates it automatically for me. What about 20 people are millionaires out of the 100? There we start to get, remember, e to the -6 is basically 0. So we can play around with it if we use the cell references like that. So we'll pick up here like next class. We'll do some more work in Excel with a binomial equation. We'll talk a little bit more about that, and then we'll jump into our kind of final topic, which is the Poisson distribution. Okay? All right, so we'll end it there today. If you have any questions, I'll leave the Zoom open. You can ask some questions as people are heading out. Otherwise, stay safe out there. Hopefully, I'll see a lot more of you here on Thursday if the roads are clear.